Hi guys, I'm Mr. Joseph, your chemistry teacher. I'm back with my lectures. So in today's lecture, we'll be looking at mass spectrometry as an analytical technique and a brief explanation of the operation of the mass spectrometer. Then we're going to look at the concept of isotopy and identification of isotopes, then interpretation of mass spectrum, and how we can deduce what isotopes and relative abundance of what isotopes from the mass spectrum. Then we're going to calculate the relative atomic masses of elements. Then we're going to define relative atomic mass, relative isotopic mass, relative molecular mass, and relative formular mass in terms of what the unified atomic mass unit. So please, I want you to listen attentively and get the best out of today's lecture. Thank you very much as you listen. So we are looking at mass spectrometry, which is an analytical technique that was initially used to show the identities of isotopes. When we talk about mass spectrometry, is the use of mass spectrometer, and it was initially used to show the identities of isotopes. It is now used to calculate molecular masses and even characterize new compounds. Also determine the relative atomic masses of elements. So the first mass spectrometer was built in 1918 by Francis, a student of J.J. Thomson, the man who discovered the electron. I believe must have done that. He used the instrument to show that there were different forms of the same elements, which we now call isotopes, which are atoms of an element with the same atomic number, the different mass number. So we discover isotope through mass spectrometry as an analytical technique. So isotopy is a product of mass spectrometry. In fact, it was mass spectrometry that revealed the phenomenon of isotopy, whereby atoms of the same element will have different masses, with the same atomic number, or with the same number of protons. So the observed was a consequence of the abundance of each of the isotope. So from mass spectrometry as an analytical technique, we were able to discover isotopes. And what is an isotope? Isotopes are atoms of an element with the same atomic number but different mass numbers. The same atomic number but different mass number. Then in terms of subatomic particles, in terms of the fundamental particles of an atom, isotopes are defined as atoms of an element with the same number of protons but different number of neutrons. When we talk about fundamental particles of an atom, there are protons, neutrons, and electrons. So in terms of subatomic particles, isotopes are atoms of an element with the same number of protons but different number of neutrons. As you can see, this is a typical example of isotope. We have chlorine 35, 17, and chlorine 37, 17. The same atomic number, the different mass number. The same number of protons, which is 17, and proton 17. Different number of neutron. Neutron here is 18, and neutron here is 20. So that is what we mean by isotopes. This is an example of an isotope. We have other examples. They have the same number of protons, different number of neutrons, the same atomic number, different mass number. So having considered mass spectrometry as an analytical technique, which is the use of mass spectrometer, we want to look at the operation and the component of a mass spectrometer. Now in a mass spectrometer, what happens is that the particles, it can be an element, it can be a compound, they are vaporized and turned into positive ions, which is ionization. So the sample is first of all vaporized and is turned into positive ions. So you pass it through the ionization chamber, where high energy electron gun knocks off electron from the particle, knocks off electron from the element, knocks off electron from the compound to form what we call molecular ion. So through that process is what we call ionization process. So an ionization process takes place what in the what ionization what chamber. Now the ions are accelerated. It goes to the analyzing chamber where they are separated. It passes through an electric field. So the ions are accelerated and focused into a beam, which is then deflected by what? By the magnetic field. So the electric field causes what? Causes the ions to what? Accelerate and focus into a beam, which is then deflected by what? A magnetic field. So when they get to the magnetic field, the magnetic chamber, the chamber where they are what? Deflected. And the deflection is based on what? Their mass to charge ratio, otherwise known as what? The atomic what? The atomic mass. So particles with a large mass to charge ratio or atomic mass value are deflected the least, while those with what? A low atomic mass or mass to charge value are deflected what? Are deflected the most. After which it gets to the detector. So the detector records each species or each ions as a peak on what? On a trace. So the value of the mass to charge ratio, which is the atomic mass for each species, can be read from what? Its peak position on the trace. So what happens is that the results produce what? A mass spectrum. It will give us a graph which we call what? A mass spectrum that portrays the different ions in order of what? Their mass to charge value, or in order of their what? Atomic mass. So the mass spectrum produced shows what? The relative abundance of each of what? Of each of the ions. If it's an element, it will give, or it shows what? The relative abundance, which is the isotopic abundance on the vertical axis, and the mass to charge ratio on the what? On the horizontal what? On the horizontal axis. So the mass spectrum is a graph of what? The relative abundances against what? The mass to charge ratio. So the isotopic abundance with the relative abundance of each of what? Ions, or each of the isotope, is on the vertical axis, which represents the relative abundance. Then the horizontal axis shows what? The mass to charge what? Ratio of each of the isotopes, or each of what? The ions that is what? Involved. So this is the what? This is the process involved in the operation of what? The mass what? The mass spectrometer. You are still going to do more of it in your what? In your A2. So this is just what you ought to know when it comes to what? Mass spectrometry as an analytical what? Technique, which involve the use of what? Mass spectrometer. So as you can see, this is a diagrammatic representation of the mass spectrometer, showing you different components, different parts of the mass spectrometer. Now this is the heated filament that produces high energy electrons that knocks off electrons from the sample, that causes the sample to what? Undergo ionization, whereby it produces what? The molecular what? Molecular ion, and can still undergo what we call fragmentation. You are going to do more of that in your A2. So this is the ionization chamber where ionization takes place. This is the sample. The sample must be in its vapor state, where the sample is what? Vaporized. You have an oven, coupled with what? The mass spectrometer that what? Vaporizes what? The sample, if the sample is solid or what? Or liquid. So this is where the ions, positively charged ions, are what? Accelerated after what? After the ionization. So this is the region where acceleration takes place. I think it's around the electric field. Then you get to the magnetic field where they are what? Deflected according to their what? Mass to charge ratio, or atomic mass. The ones with the heavy, those heavy isotopes, or those ions that have what? Heavy mass to charge ratio or atomic mass, will be deflected what? The least, while the lighter ones will be deflected what? The most. Then now gets to the what? Ion detector, where it gets to the recorder. The recorder now from the recorder it gets to what? A computerized, gets to the computer, where it produces what? The mass spectrum, which will produce what? A graph of what? The relative abundance against the mass to charge ratio, or the relative abundance against what? The atomic what? Masses of each of what? The isotopes, if it's an element, or the relative what? Ions, if it's a compound, or what? a molecule. So this is just a typical diagrammatic representation of the mass spectrometer and how it operates. We are going to look at the mass spectrum of different elements and different compounds as we proceed. So here's the mass spectrum of neon, which is an isotope, which is a product of mass spectrometry from mass spectrometer. So it shows a graph of the relative abundances of the elements against the mass to charge ratio atomic mass. That means neon is an isotope. It's an isotopic element. It's an element that exhibits the phenomenon isotopy, which was revealed during mass spectrometry. So it will give us a graph of the relative abundance against the mass to charge ratio, or the atomic masses, with different peaks representing the isotope. Like for that of neon, you can see the peak neon 20, neon 21, and neon 22. You can see neon 20 is the tallest peak. That is the peak. The tallest peak is the most stable peak, which is the peak that have the highest relative abundance. That the most abundant peak is the tallest peak. Then you have neon 21 and neon 22. The relative abundance of neon 20 is 90.9, which have the highest relative abundance, which is the most stable peak. Then neon 21 is 0.3%, and neon 22 is 8.8%. Now what happened is that the peak that have the highest mass to charge ratio, or the highest atomic mass, is the heaviest peak. So the heaviest peak is neon 22, which have among the peaks, it has the highest mass to charge ratio, or it has the highest atomic mass. So neon 22 is the peak with the highest atomic mass, or highest mass to charge ratio. So with the relative abundance and the isotope, you can easily calculate the atomic mass of neon as an isotopic element. We call it the average mass. That's what we call it relative abundance, because the atomic mass is calculated based on the relative abundance and also the isotopes. So if you look at, you discover that it gives us a graph of relative abundance against the mass to charge ratio. It can be a graph of the height of the peak against the mass to charge ratio. It can be a graph of the detected current against the mass to charge ratio. It depends on the mass spectrometer. Some mass spectrometers are calibrated in abundance, relative abundance, which is a percentage. Some mass spectrometers are calibrated in terms of height of the peaks, which is a different result that will be given. Then some mass spectrometers are calibrated based on detected current against mass to charge ratio. So that is how you can interpret the mass spectrum of an isotopic element. Once you can interpret the mass spectrum effectively, you can easily calculate the relative atomic mass of that particular isotope. So this is the mass spectrum of lead, which is an example of a mass spectrum that can be obtained from a mass spectrometer, and it's quite slightly different from the previous one we just consider. So this, you can see that it gives us this is a mass spectrum with a graph of detector current against the mass to charge ratio, or atomic mass. So on the vertical axis we have the detector current, while on the horizontal axis we have the mass to charge ratio, or the atomic mass. And you can see that lead have 4 isotopes. There are 4 isotopes of lead from the peak. If you look at, we have lead 204, lead 204, lead 206, lead 207, and lead 2008. So which are isotopes of lead. So we have 4 isotopes of lead from the graph. You can see that the isotope with the tallest peak, with the highest peak, the tallest peak, is the most stable isotope. and it have what the highest what detector current is the most stable what the most stable peak, and the peak that have the highest mass to charge ratio or atomic mass is the heaviest isotope. So lead what lead 208 is the heaviest what isotope because it have what the highest what atomic mass or mass to charge what to charge ratio. So that is how you can easily interpret the mass spectrum of a particular isotopic element. So the tallest peak is the most stable peak, and that is the peak that have the highest detector current. Then the heaviest peak is the peak that have the highest mass to charge ratio or atomic mass. So you can see that lead 208 is the most is the heaviest peak, is the isotope that have the heaviest is the heaviest isotope. So that is that. It's as simple as A, B, C. So this is the mass spectrum of boron. Another example of a mass spectrum. So just as I said, it depends on the mass spectrometer. So how calibrate depends on the calibration of the mass spectrometer. So as you can see, this one gives a graph of the height of the peak against the mass to charge ratio. Now from the mass spectrum, you discover that we have two isotopes of boron, which are boron 10 and boron 11. So just as I said that the peak, the isotope with the highest mass to charge ratio is the heaviest isotope. So boron 11 is the heaviest, while the isotope that have the highest, the tallest peak is the most stable one, the most stable isotope. You can see that boron 11 is also the most stable isotope. It have the highest peak. That is the isotope with the highest peak, which is the height of the peak. So that is the most stable. The isotope with the tallest peak have the highest height is the most stable, while the heaviest is the one that have the highest mass to charge ratio or atomic mass. So it can come in various forms. So it depends on the mass spectrometer and how this mass spectrometer is calculated. All you need to do is to interpret the mass spectrometer effectively and get the right figures so that you can easily calculate the relative atomic mass of the particular element. So it is very, very important. Interpretation of the mass spectrum is very, very important. You can convert the height of the peak to percentage. Just do your normal ratio and convert it to percentage and use it to calculate the relative atomic mass of the element. So to calculate the relative atomic mass of an element, we use the formula, the isotope and the abundances from the mass spectrum. So once you interpret the mass spectrum and you get your figures from the mass spectrum, you get the relative abundance and you get the isotope, or you get the height of the peaks on the isotopes, or you get the detector current and the isotope. You can easily calculate the relative atomic mass. In the mass spectrum, the vertical axis might be in percentage, which is the relative abundance. It might be in normal figures, which is your height of the peak. So to calculate the relative atomic mass, what you do, the relative atomic mass will be equal to isotope 1 times abundance 1 plus isotope 2 times abundance 2. If it's up to 3, isotope 3 times abundance 3 divided by 100 if the relative abundance is in percentage. If the total sum of the abundances is equal to 100. Or you can use this one, isotope 1 times abundance 1 plus isotope 2 times abundance 2 divided by the total sum of the abundance. You do this in a situation whereby the sum of the abundances is not up to 100. Then, or you can use this isotope 1 times abundance 1 plus isotope 2 times abundance 2 divided by the total sum of the relative height of the peaks. So it depends on the mass spectrum. So that is just that. So it's as simple as A, B, C. You can have up to 5 isotopes. So you say isotope 1 times abundance 1 plus isotope 2 times abundance 2 plus isotope 3 times abundance 3 plus isotope 4 times abundance 4 plus isotope 5 times abundance 5 divided by what? The total sum of the relative height of the peak, or the total sum of what? Of the abundance. So once you use the formula correctly, you get your right answer. All you have to do is to interpret the mass spectrum very, very well. You get the abundance, you get the isotope, then you can easily calculate what? The atomic mass, which is the relative atomic mass. So if you are given the mass spectrum and asked to calculate the relative atomic mass or percentage abundance of the elements, the first thing to do is interpret the mass spectrum, of which we've done that. Deduce the isotopes from the mass spectrum. Yeah. Deduce the abundances or relative heights of the peak from the spectrum. Then use the above formula to calculate the relative atomic mass of the element. So these are the steps you have to take. Once you take these steps, you get what? You get the right answer. So in trying to determine the relative atomic mass, scientists have chosen to use the isotope of carbon, which is carbon 12, as the standard, which has been assigned a mass of exactly 12 units. So the mass of other atoms, other elements, is found by comparing their masses with the mass of what? The mass of carbon 12. So we call this the relative atomic what? Atomic mass. Relative atomic masses of what? Elements. So what is relative atomic mass? So it is the mass of an atom relative to carbon 12 isotope having a value of what? 12 units. Just as I said, the scientists that decided to what? To use isotope of carbon, which is carbon 12, as the what? As the standard. So, the mass of other elements are compared to that of what? That of carbon 12. So the relative atomic mass is the average mass per atom of an element over what? Mass of one atom of what? Carbon 12. So carbon 12 is used as what? As a reference what? As a reference standard. So relative atomic mass, which is AR, is equal to what? The mass of an atom relative to what? Carbon 12 isotope having a mass of what? 12 units, or it can be represented in this form. So it's as simple. So now we'll have relative isotopic mass. We're still on carbon 12, as the standard. So relative isotopic mass is the mass of an isotope relative to carbon 12 having a value of what? Having a value of 12 units. So you can see the relative isotopic mass, the mass of an isotope relative to carbon 12 isotope having a value of what? 12 units. Then if it's a molecule, we say relative what? Relative molecular mass, which is the mass of a molecule like chlorine, a molecule like ammonia, a molecule like carbon dioxide, a molecule like what? Carbon monoxide, and the rest, etc. So it is the mass of a molecule relative to carbon 12 isotope having a value of what? 12. We say relative molecular what? Molecular mass. Basically covalent compounds, they exist as what? Molecules. So when we talk about relative molecular mass, we use the symbol Mr to represent molecular mass. It is the mass of a molecule relative to carbon 12 isotope having a value of what? 12 units. Then we have relative formula mass. This is when we are referring to what? Ionic what? Compounds. Substances that are made of what? Ions, positive and negatively charged ions. So it is the mass of a species or mass of what? Or an ion relative to carbon 12 isotope having a value of what? 12 units. We'll talk about ionic compound, talk about sodium chloride, calcium fluoride, and it's just etc. and the rest. Talk about ionic compounds, ammonium ion, talk about ions, and what? Ionic compounds. Talk about relative formula mass. So relative molecular mass and relative formula mass, they are still the same. When we talk about relative formula mass, we are referring to what? Ionic compounds. We'll talk about relative molecular mass, we're talking about molecules, covalent molecules. When we talk about relative formula mass, it has to do with what? Ions, positive and negatively charged ions. So it's the mass of an ion relative to what? Carbon 12 isotope having a value of what? 12 units. So this is an example for us to solve. It's a typical examination question. So you are given what? The mass spectrum of an element, and all you have to do is to interpret the mass spectrum effectively, and you are asked to calculate the average relative atomic mass of neon using the above what? Information. So the above information is the mass spectrum of neon, which is the graph of the abundance in percentage against what? The mass to charge what? Ratio. So for us to interpret the spectrum, you can see that it contains what? 3 isotopes of what? Neon, which is neon 20 with abundance 90.92, neon what? Neon 21, and neon what? 22. Neon 21 have an abundance of 0.26. Neon 22 have an abundance of what? 8.82. So having identified the what? Isotope and the abundances, so all we need to do is to apply a formula to calculate the relative atomic mass, which will now be equal to what? Isotope 1 times abundance 1 plus isotope 2 times abundance 2 plus isotope 3 times abundance 3 divided by what? Divided by 100, which is the sum of what? The abundance of the isotope. So if you add the abundance 1 plus abundance 2 plus abundance 3, the total sum will be equal to what? 100. So you divide by what? 100, because it's already in what? In percentage. So if you look at the average relative atomic mass is this abundance 1 times isotope 1, abundance 2 times isotope 2, abundance 3 times isotope 3, divided by what? 100. So you get 20.179, which is approximately what? 20.18. So this is, which is what? The relative what? Atomic what? Atomic mass. So as you can see, it's as simple as ABC. All you need to do is to interpret the graph effectively, interpret the graph very, very well, identify the isotopes, identify the relative abundances, and you apply what? Apply the formula. So I advise you to solve as many questions as possible, attempt as many questions as possible, and feel free to reach out to me if you encounter what? Any difficulty. So I'll be leaving a task with you, so please attempt it and reach out to me if you encounter what? Any difficulty. Thank you very much for listening, and please make sure you attempt the question I give you and attempt as many questions as possible. So this is the task. I want you to attempt this task. It's a typical examination question. Please attempt this task and solve as many questions as possible. It's as simple as ABC. So the question before us is, look at the mass spectrum of germanium. Just interpret the mass spectrum. Then write the isotopic formula for the heaviest isotope of germanium. Then use the percentage abundance of isotope to calculate the relative atomic mass of what? Germanium. So it's as simple as what? ABC. Say, attempt this question. If you have any difficulty, if you encounter any difficulty while trying to solve the question, please feel free to reach out to me. I'm Mr. Joseph, your chemistry teacher. I'm always there for you. Please subscribe to my YouTube channel, share, comment, like, and reach out to me if you encounter any difficulty. I'm Mr. Joseph, your chemistry teacher. I'm always there for you. Thank you very much for listening. I'm Mr. Joe, your chemistry teacher. Thank you for listening.